Okay, are there any questions for me before I begin? No, today it's going to get a bit mathematical, and it'll continue to be mathematical as we go along. But it's a kind of a review. If you have seen vectors in any undergraduate math course, and statics and dynamics and stuff like that, you should be okay with it. Let's just review briefly what we saw in the. Did I start recording? I hope so. Okay. We saw basically the constitutive equations. Okay, the fluid mechanics is part of a continuum mechanics. So we are looking at material as being part of a continuous medium. So when we talk about a concentration at a particular point, the concentration is treated as a continuous variable in space. The temperature is treated as a continuous variable in space, and so is the velocity. But there is a similarity in these three phenomena, the so-called unified way of looking at transport phenomena at the molecular level, the way that they exchange mass or heat or momentum due to molecular interaction. And because we are not looking at it, we said we are going to write these constitutive equations that captures what happens at the molecular level. And so these are called just constitutive empirical equations. Not all materials need not obey them. And we saw examples of non-Newtonian fluid as well. Then we talked briefly about the interfacial phenomena in the last lecture. So when you have a definite interface between two immiscible liquids or a liquid and a vapor, because once again of the differences in the molecular properties on either side of that interface, you will have a dynamic condition that has to be satisfied. That is, the force balance, the pressure jump across such a curved interface is proportional to the curvature. Del dot n is a vectorial way of representing the local curvature. So this is a very general expression for any arbitrarily shaped interface. And this introduces a new property called the surface tension. Just like in the previous case, we had this equation defining diffusivity, second equation defining thermal conductivity, and this equation defining viscosity. The Young-Laplace equation defines a new property called the surface tension, which is a manifestation of imbalances in forces at the molecular level at an interface. And that is the property, and 1 over R1 and 1 over R2 are two principal radii of curvature. Then we moved on to examining force balances under static conditions, and we showed that the pressure is isotropic, meaning it is the same in all directions. And we derived the hydrostatic equation, gradient of P equals minus rho G. So what are the assumptions? That there is no motion under static condition, so no velocities, and there are only two forces, pressure and gravity. How do they balance in a fluid that is stagnant, okay, and a gravitational field? And that is again a vector form of the equation. There are three components in there. So that you should be able to expand, okay? And when you do that and integrate the equation, that's a differential equation. So when you integrate that equation, you get an expression for the pressure variation. That is P equals P0 minus rho G Z. I should have a Z there. Okay, so Z is measured going up and G is acting vertically down in that direction. So you pick a reference point and call the pressure at that reference point as P0, and then you have that particular expression for pressure variation. An important consequence of this, we did this think, pair, share exercise. What did you think of it? Was it useful or was it waste of time? Over 7 minutes, 8 minutes. It was useful. We will try to use it as much as possible. It is a new technique, I guess, that I've learned recently. But in this course, it's going to be a bit more hard because we will have a very logical, continuous elaboration of a mathematical technique, for example, in analyzing a particular problem. Whenever we get into conceptual thinking, that would be a good place to break and take a break the monotony in the class and go through that exercise. And particularly what I asked you to do in that exercise is derive the magnitude of the buoyancy force. Okay, so let me ask you, what is a source of a buoyancy force? We said when we started this course, there are only 4 forces, right? Gravity, electromagnetic, strong and weak nuclear forces. We are not going to talk about strong and weak nuclear forces. We are going to talk about gravity and electromagnetic. We are not really going to talk about electromagnetic force per se, but the electrostatic interactions between molecules gives rise to a lot of other forces that we are talking about. Shear force. Shear force is nothing but a manifestation of interaction between molecules, which is due to the electron cloud interaction between molecules. Surface tension is the same thing. Now we are talking about buoyancy force. Later on we'll talk about drag force, we'll talk about added mass force, etc. What are these forces? Where do they have their origin? So where does buoyancy have its origin? The
pressure difference.
The pressure difference. It's very important that all of you understand that. It's not a magical force, it is a consequence of the pressure variation on a submerged object. So if I have a pen in air, does it experience buoyancy force?
Yeah.
In principle it does, right? But is it going to be strong? Why? Because density of air is very small. Buoyancy force is the weight of the fluid displaced. So if I know the volume of this pen, I can calculate the weight of air occupied by that pen. That is the fluid that is displaced. Because air density is so small, buoyancy force here is very low. So if I drop it, its weight is so much that it will fall. But if I take, this is made of plastic, most likely less dense than water. So if I throw it on water, what would happen? It would float. Why? Because the buoyancy force there is much stronger, and if the weight is lower than the buoyancy force, it floats. If the weight is greater than the buoyancy force, it will sink. If the weight is the same as the buoyancy force, what happens? It will just be suspended where it's called neutrally buoyant. So wherever you leave it, it will be happily there, staying there, because forces are balanced. The weight is balanced against the buoyancy force. So if I have such a neutrally buoyant particle immersed in a tank somewhere here, it will be there happily at rest forever until I come and give it a push. So if I give it a push and move it there, what will happen? Why?
The force is balanced, so it doesn't matter where it is.
Right.
So it can move at a constant speed.
Right. If I give it a push, it'll start moving. Okay, downwards. That's what you are saying. That's correct. Will it continue to move until it hits the bottom? Depends on what is the magnitude of the force I gave. But when I give it a magnitude of force, is there any other force that is stopping it from moving? These are the thought experiments that you can continuously do while you're taking a bus, while you're driving. So the fluid mechanics becomes second nature to you, right? So if the particle is moving, there is a relative velocity between the particle and the fluid. And that means there is a shear, there is friction. Okay? So that's what is going to bring it down to a stagnant position again. Okay? So you give it an impulse, and it starts moving. And the moment it starts moving, there is a drag force that opposes its motion. Okay? And drag force basically will dissipate all the energy that the object has. So it will reach a new position and it becomes at rest. Now, will it start rising up again? That's a very good observation. If you get that, you get buoyancy force completely in your mind. Okay? So here I said, for example, what is the pressure at 1 and the pressure at 2? Which one will be higher? Pressure at 2 will be higher because you have a gravitational head above that, right? So, does that mean that the buoyancy force experienced at this level is higher than the buoyancy force experienced at that level? Very good. You know, I have a very bad habit of, if I hear one right answer from one person, I assume that everybody understands and I keep on moving, asking more and more questions. If you guys don't understand an explanation Or somebody says yes and I say good, and then I move on to the next. You hold me, you say no, it's not good, stop it, and explain why that is the case. Okay? If it is not clear. If it is clear, then we'll keep on moving. Okay, so the answer is it's going to be the same. The buoyancy force is going to be the same here and here, right? Because one way we understand it is buoyancy force is the weight of the fluid that is displaced. Weight of the fluid that is displaced is the same at both locations, so the buoyancy force must be the same, and its weight hasn't changed in going from one level to the other level, so it should be at rest. So a neutrally buoyant particle will remain at rest wherever you position it. Okay? The fact that the pressure here at 2 is higher than the pressure at 1 doesn't change the buoyancy force. But it is true that the pressure at 2 is higher than the pressure at 1. Right? Why is that? If I design a submersible boat and I take it deeper and deeper into the ocean, and at any point I can add water or release water to make its effective density the same as the surrounding one. So I can make it neutrally buoyant. If you look at submarine designs, these are the issues that you need to worry about. Okay? So I want to go from one level to another level. How do I do that? And then at that level I want to just stay for a while. What do I do? Okay? So you need to constantly take in and out water to adjust your weight to be equal to the buoyant force. Then you can stay at that level for a while, right? But at a deeper level, the pressure surrounding that object is going to be much higher. So when you're designing the mechanical shell, you need to worry about at what depth you are. But the buoyant force is going to be essentially the same if you want to achieve neutrally buoyant status. The reason is it is the difference in pressure that matters. Okay? So the difference in pressure as you go around and the difference in pressure as you go around here is what causes the buoyancy force. Okay? And that's why it is the same. Any questions? Okay, let's then move on to make the math a bit more difficult. Okay? The idea is going to be the same, but I want to make the math a bit difficult. The last time I made the math very easy by telling you calculate the buoyancy force on a cube. What did you have to do in your in your experiment, think, pair, share experiment? You needed to calculate the force on the top surface. You needed to calculate the force on the bottom surface, and the difference is your buoyancy force. Because the force acting on the sides cancel out, right? So we pick the surfaces in such a way that you have a flat, uniform surface. All the forces are pointing in the same direction. So all you have to do is take that force at the top surface, which is a constant pressure, multiplied by the area, gives you the force. So you can do it algebraically. This is what one would do at the undergraduate level. Everything is simplified to algebraic equations because you don't want to deal with differential equations. Here you have to deal with differential equations. So I'm going to ask you to calculate the same buoyancy force on a spherical particle. Okay? So this is the situation. So you have a fluid and you have a sphere of radius A that is submerged in the fluid. Calculate the buoyancy force. You already know the answer. What is the answer? It is the weight of the fluid that is displaced. It doesn't depend on the shape. But how do you prove that it is the weight of the fluid so that it doesn't depend on the shape? How do you calculate the net buoyancy force? Okay, mathematically, how do you do that? You should be able to develop those skills in this course. Okay, so help me out. How would I start? Set up a coordinate, set up a reference frame. Okay, so here I'm saying I'm going to start measuring from the center of the sphere. Z is vertically measured up from the center of the sphere, and from the top of the sphere, the fluid level is H. So I know what is the head, and at this stage, the pressure at the free surface, I'm going to call this as 0. So I'm start to measure the pressure, the reference pressure at that point. So I know that P is equal to P0 minus rho gz. That is in general the pressure variation. Okay, so I need to find out what this P0 is in this case. So for example, if I start measuring the distance from this point, H plus A, from the reference point, that is put Z equals H plus A, what should be P equal to? The general expression for this, you know how we get this? We get this from integrating this equation, dP dz equals minus rho g, which comes from this equation, gradient of P equals minus rho g in vector form. So when you expand that in a scalar form, you get this, and when you integrate that, you get this, with P0 being the integration constant. Okay, so the first thing is we need to find what the integration constant is. That depends on where you have put the coordinate and how you start measuring. Okay, so this is an algebraic expression that relates the pressure with respect to height, and when I put Z equals h plus a, that is, I'm talking about the free surface, I should know what the pressure is. From that, I have to determine what my P naught is in that expression. Okay, so when I put h plus a, P is equal to 0. The pressure at the free surface is 0. So I'm dealing with gauge pressure, if you like. It's kind of open to atmosphere. Okay, so I will get P0 as equal to rho g times h plus a. So my expression for pressure is P equals rho g h plus a minus rho g z for this particular reference frame. And you can always verify it. For example, when I put z equals h plus a, I get P equal to 0 at the free surface. When I put z equal to 0, what do I get? Z equal to 0 is this plane, right? That's where my center is, my origin is. So the pressure is rho g times h plus a, which is what I would expect. Okay? So I have an ability to calculate the pressure at any height, z. Okay? So in order to calculate the buoyancy force, what I need to do is I need to know what is the pressure at every point on the surface and in what direction does it act. Okay? So we know that the pressure always acts normal to the surface. So I've indicated by red arrows, the direction of the pressure force. Okay? So if I take at the bottom point, the pressure is going to be acting like this. Okay? If I take the top, the pressure will be acting on that. So I need to take the component of this pressure. For example, when it is particularly at this point, I need to decompose that into the horizontal direction and the vertical direction. In the horizontal direction, if I take another arrow at the same side, opposite side, I will have an opposing force. So the horizontal forces will cancel out. So this sphere is not going to move horizontally. Okay? But it will experience a net vertical force. Why? Because the vertical force at the bottom is higher than the vertical force at the top. Okay? So I need to devise a mechanism, a mathematical way of adding all these forces up, that is integrating the force. Okay? And the way that we do that is by starting with this equation. Okay? What does this equation tell you? The differential force acting on a surface is equal to the normal to that surface multiplied by pressure times dA. Okay? So this is at a local point. So if I have a sphere, what I'm going to do is I'm going to take a differential ring going around it. On that surface, I'm going to have a pressure P that acts depending on its position Z. That pressure will depend on where that surface is. Okay? So, does anybody have a question on this equation? I'm talking about that equation. How do you come up with that? Because these are translations of conceptual ideas into mathematical language so that we can process it further to get the answer. So what conceptual idea that it translates? That the differential area acting on a surface is the pressure times the differential force is the pressure times the differential area. Because pressure is force per unit area. Okay, so if I multiply by the area on which it acts, I get the net force that acts on this ring that I have indicated here. But remember that pressure is going to change depending on which ring I am taking. So I need to take a series of rings from the bottom to the top and add them all up vectorially. I need to add them up vectorially. Okay? And that's where I need to convert this differential into an integral. So I will write this as integral of df equals integral of npdA. Now integral of df is nothing but f. But integral of npdA, I need to work out each one of those terms. And this is very important because we're going to be seeing this again and again. Once you understand it with a simpler problem like pressure, you should be able to apply the same thing to stresses. When we do the stress tensor, for example, what is the shear force on a surface like that? Same ideas apply. except you're going to replace pressure by the shear force. The beauty about the pressure is it's simple in structure. It has only a normal component, whereas the shear, you need to worry about which component of the shear that you're dealing with. There are 9 components, whereas with pressure there are only 3 components based on the normal. Any questions so far? So we talked about this idea of the pressure at any point having a vertical component and a horizontal component. We don't want the horizontal component. We want only the vertical component. Buoyancy force is the vertical component. So how do I get the vertical component? I take the unit vector in the direction. So the unit vector here is IZ. IZ dotted on F gives you the component of the force in the Z direction. Again, I keep repeating this, okay? I don't want to repeat it too many times, but if anything that I say is not clear, just stop me and ask me to explain it, okay? So the dot product of the force in the direction in which you want to resolve gives you that component of the force. So in this case, F is a force that can in general be an arbitrary force in an arbitrary direction. So particularly in this case, it's a force acting in this direction. And if I want its component only in the vertical direction, I dot it with IZ. If I want its component in the x direction, what do I do? Dot it with IX. If I want it with y, I dot it with IY. Okay? So a dot product between 2 vectors gives you what? Do you know what a dot product is? Been a while? Okay. That's what is coming next. I need to review all these things. But I wanted to do the buoyancy before I go into the vectors and the tensors review of that. A dot product has a mathematical definition. But physically what it tells you is it gives you the component of the force in the direction in which you are dotting it with. Okay? That's a symbolic way of expressing that I am taking a component of the force in a particular direction. It basically comes from trigonometry. Okay, so what is it? Does anybody remember the definition of a dot product? If I have 2 vectors and another vector B, what is the dot product? What is the meaning? How do I calculate it? What is the algorithm? And what is the physical meaning? Where do I use it? Why did I define it? We define a lot of these products, okay, because they're going to be useful products. If you think about it, why is 1 plus 1 2? We develop those algebra, right? We develop those arithmetic because they're going to be useful to us. There is a binary arithmetic, right? There is a various other forms, hexadecimal, octal. These are all number systems that are different from the decimal system. Okay? And you can create arithmetic in those systems too. So I can say 1 plus 1 is 0. Right? So it depends on what we want to do. So there is a purpose for defining all the symbols. That part you have to accept it and become familiar with it. So it is like learning a new language. Okay? Mathematics in some sense is a new language. It allows us to set up problems, think about concepts, set up problems, and solve problems. So A dot B, the definition of it, there are several definitions. We will see that pretty soon. But since I'm talking about dot product, let me introduce this. It's going to be simply A, B, cos theta. Okay? So you can think of it as projecting the vector A onto B or projecting the vector B onto A. Okay? So it is a scalar quantity. A and B are vectors, but the dot product is a scalar quantity. So in the same sense, IZ dot F is going to be called that as the Z component of F. It is the right hand side that we need to work. So you have an integration there. IZ dot N. Okay? So N is a vector like this, the normal, and IZ is a vector like this in the Z direction. Okay? So I need to set up, again in this coordinate, I started measuring Z this way. So let me start measuring theta this way, the angle theta. Okay? So if I take this vector n that you see there, I'll highlight it in red. That is the normal vector, okay? And I want to decompose that vector into in the x direction and in the z direction. So if I define this angle as theta, that angle is going to be theta. Okay. So what do you think would be the relationship between n and iz? Sine theta, trigonometry. You cannot afford to project. You need to build on these things. Okay. So n cos theta will be the horizontal component, and sine theta will be the vertical component, right? So iz dot n is going to be sine theta, where theta is defined as the angle measured from the horizontal. So you have figured out what this component is, iz dot n. Okay. The next thing you need to figure out is what is dA. What is dA? Differential area of a ring that goes around it. So if you take that circle that goes around 2 pi, what will be the circumference? 2 pi r. But what is r there? R, very good. You are already ahead. Okay. So I'm just thinking of this as A. A is the radius of the sphere. So 2 pi r, this is r. Okay. So 2 pi r is the circumference times that arc length. Are you following me?
Okay, A is the radius of the whole sphere.
A is the radius of the whole sphere. Whichever direction you go, it's
R
R is the radius at that particular radius from the center of the axis to the surface at that particular height. So that R is going to be a variable. It's going to change with a Z. Okay. So what will dA be? The differential area is going to be 2 pi R times the differential arc length ds. Okay. What do I mean by ds? It is the arc length of that particular strip. What would ds be? A d theta. Right? ds is going to be a d theta. Now a is a constant, but r is not. So what is the relationship between r and a? That is r. Okay. So what is the relationship between r and a? R is equal to a cos theta. Okay. So you have figured out an expression for I dot n. You have figured out an expression for dA. And dA is in terms of d theta. It's still a differential. Okay. So dA is going to be equal to 2 pi a square cos theta d theta. Okay. The last is the expression for pressure, which we already figured out. Okay. And that expression is P is equal to, what was it? Rho g h plus a minus rho g z. Rho g h plus a minus z. But what is z in terms of theta? Z is a sine theta. Okay. And why are we doing it in terms of theta? We want to integrate over the entire sphere, and we have chosen to express everything in terms of theta. You can choose to express everything in terms of dz if you like. Okay, that's a choice that you make, because these are all related after all. But in this particular case, I'm showing how to set up the integration in terms of theta. So the last step that you need to do is plug all these in. So f of z is going to be equal to integral of sine theta times rho g times h plus a minus a sine theta multiplied by 2 pi a square cos theta d theta. A simple idea expressed vectorially, a simple equation, but when you have to calculate it, you need to figure out each one of these, how they vary. And that's not an easy integration. This is where Tom's help will come in handy on how to do this in Maple or MATLAB, because you need to do the integration. What would be the limits for the integration? from minus pi over 2 at the bottom of the sphere to plus pi over 2 at the top of the sphere. In an exam, if you get it to that stage, I accept. You don't need to do the integration. Okay? But in an assignment, I would expect you to do the integration because you have access to tools. I'm not expecting you to remember anything. What I expect you to do is understand and develop ideas logically. Okay? So if you give me this, I know you can get the answer. From this point on to a number is not that difficult. But to jump through all these concepts and getting at this equation is not an easy thing, and that's what I want you to be able to do. Okay? Any questions on that? Yeah.
If we go back to the equation df equal to the normal vector times this one. The direction of the normal vector is outward.
Right. Exactly. The sign that you get for df eventually, if it is positive, it would mean that it is pointing in the positive z direction. If it is negative, it would mean that it is pointing in the negative z direction. But it will carry the same sign as n, the component of n in the vertical direction. Okay? So that component of the vertical force on the top surface is going to be pointing down, but on the bottom surface is going to be pointing up. So on the bottom surface, on the average, it is higher. So the net force is going to be pointing upwards. Okay. Now there is a nice tool. I don't know whether Tom talked to you about it. It's called, I guess I don't have the internet connection here. It's called Wolfram Alpha. Okay, it's available from any browser. So you really don't need MATLAB or Maple or Mathematica on your computer. You just need a browser, and there is actually in Chrome browser there is a tool called Pi. If you click that Pi, it'll open up something called a ChE calculator. It's nothing but an interface to Wolfram Alpha. Wolfram is the guy who developed Mathematica. Okay, so he's kind of making whole Mathematica tools available to you through the internet. And if you plug in here any expression, symbolic expression, it'll actually evaluate that and send you the result. Okay, so in an assignment, you can certainly use this. Of course, you have access to Maple. You can use Maple as well. But here I've just shown how this is done. All you have to do is type integral of whatever expression that you have. Okay, and then hit return, and it will actually give you the integrated result from that. And that's how I got this result. In fact, at the end of this page, I probably have right there. You have. Okay, so if you type exactly this, or a variation of the right syntax in Maple or Mathematica or whatever language, but this one will work in Wolfram Alpha. Okay, so that is the expression that we just figured out: h plus a minus a sine t. T is what I call theta. Okay, and then it returns the result as 2 minus 2 over 2a over 3. Of course, I have left out the a squared, pi a squared. Okay, so when you 2 pi a square, when you substitute that, this is just the integral. When you substitute that, you get 4 over 3 pi a cube, which is your volume of the sphere. Okay, so when you multiply that with rho g, you get the buoyant force. Okay, so this idea that the buoyant force is the weight of the fluid displaced works for any arbitrary shape. Okay, and you can in fact show this for any arbitrary shape if you can escalate the mathematics to the next level, ability to deal with vectors in a natural way. Here we are still decomposing and calculating only one component. Any questions?
So the force has since it's dependent on weight, it has its origins in gravity, like what you were asking, the first question you were asking today. The buoyant force has its origins, large force has its origins.
Right, yeah. It has its origin in gravity. Gravitational force is the source, the reason why it exists. So, in fact, that's shown in the expression. You have rho g in there. So, if I do this experiment in space where g is 0, or close to 0, then the buoyancy force is going to go down. Okay, and the way that he explained it is also fine. It has its origin in the pressure distribution around an object. Okay, but what causes that pressure distribution? Gravitational force. Because if you take this beaker and put it in space, the pressure at the top and the bottom are going to be the same. There is no pressure distribution. Okay, so either way of looking at it would be right, that the buoyancy has its origin in a gravitational field that exists. Any other questions?
Sorry, I still don't understand that as a point that equation.
The dot product?
Yeah.
Okay, I'm going to review this very soon, so hopefully it will be clear. If it's not clear, ask me again. I'll try to give you an example. Okay, I should have done this first and then given you that, but since it was logically following from buoyancy, I thought I will do that first. Well, before we start this, let me ask you maybe a variation on this, because it's still thought experiment type of question. Okay, we understand buoyancy, okay, as having its origin in the gravitational field. Okay, so gravity is a very fundamental force. Now, I'm going to give you a situation where I have a beaker, and the beaker is on a turntable, so the beaker can spin. Okay, and this is in space, so there is no gravity. It's as if I've turned off gravity and I have this liquid and I'm spinning it. Okay. First let's look at the case. I'm not spinning. If I go along a horizontal direction, will there be a pressure difference? No, right? Because dp/dx is 0. Okay, and this is in space. So if I go in the vertical direction, will there be a pressure difference? No, right? Because I've turned off gravity in a sense. Now I'm spinning it. Okay, if I go in the horizontal direction, will there be a pressure difference? What is it caused by? Centrifugal force. Okay, so if I, in such a situation, put a particle, okay, that has a density that is heavier than the liquid, what do you think that particle will do? It goes towards the wall. Yeah. If I put a particle that is lighter, it'll go to the center. Why? Because as you go out, the pressure distribution is such that the pressure here is higher than the pressure there. Right? So as I'm spinning this particle will experience a greater force this way and a lesser force that way. Okay? And if the particle's density itself is higher, then the centrifugal force that it experiences, so it will always experience a net, what we call centrifugal buoyancy. Buoyancy due to centrifugal force that is pointing inward. Just like gravitational buoyancy is always pointing vertically up. The weight is pointing down, the gravitational buoyancy is pointing up. So it's the balance that decides whether the particle is going to sink or float. Okay? In the same sense, the centrifugal buoyancy will always be pointing, pushing the particle towards the center. But its own weight may cause it to go out. So it's a balance between these two that will decide whether the particle is going to be thrown out radially or in towards the center. Very good. That's all I need. Okay, you don't have to ask. You don't have to ask a very defined question. Just ask me to explain it again. What I'm saying here is the first thing that you need to understand is that in a centrifugal force, as you go outwards, the pressure goes up. It's a common experience. If you have ever gone on a roller coaster or in a car as you're turning around, your body gets thrown outwards, right, as you're turning in. So it's a force. In a sense, we can think of it like this. If you are going in a curve, okay, the body wants to go in straight. So there has to be a force that is kind of changing the direction all the time. That is what we call the centrifugal acceleration. And that creates a pressure variation in this direction that keeps on increasing. Okay? So on the outer point, the pressure is going to be higher than the inner point. We will do a problem in one of your assignments where you figure out what this pressure difference is. In the gravitational field, it's linear, rho g z. the centrifugal field, it is rho omega square r square. It goes actually r square radially. Okay, so this pressure acting on the outer surface is larger than the inner pressure. Do you understand? That's clear, right? So if you do the integration around that using the pressure profile, you'll find that there are more forces pushing it towards the center than the force that is pushing it out. Just like in a gravitational field, there was more forces pushing it upwards than pushing it down, because the pressure at the top level is lower than the pressure at the bottom level. That's what gives rise to a net force upwards, the buoyancy force. So in the same sense, the buoyancy force in the centrifugal field will always be pointing towards the center. Is that clear? Okay. So to answer the question of whether the particle is going to go out or in, you need to compare that buoyancy force with its own weight. Because its weight will have a tendency to throw it out, buoyancy will have a tendency to throw it in, and the balance between them will decide what happens. Just the same way in the gravitational field. If I have a particle that is heavier than the fluid, the weight is bigger than the buoyancy force, so it sinks. If I have a styrofoam ball, its weight is smaller than the buoyancy force takes over and it floats up.
Okay, I didn't know that complicated, but if it's lighter, it's like it will go up. If it's lighter, so like in this case, it will be going up.
No, but we have turned off the gravity here.
Oh, okay.
We have turned off the gravity, so it will go inwards. There is pressure variation only in the radial direction. There is no pressure in the vertical direction. I can obviously superpose these two and then say, plot the trajectory of this, because then it will go in, right? It will go in, but as it goes in, it will go up, up. I guess. Right? You have a question?
You have some equations to describe this.
That's what you're going to do. Your assignment. Okay. I don't want to solve all the problems. I want to solve a few problems, show you the path, give you some ideas, and then I want you to look at some of those problems. So, a pressure distribution in a static condition in a centrifugal force field. Okay? The equation goes something like P equals P0 plus rho omega square r square over 2. Okay? You can open up Tensor and Lightfoot. They have the solution in there. Okay? Okay. So the vectors, tensors, a brief review. There are two sources, Kundu and Cohen. That's one. The other one is Tensor and Lightfoot in the appendix, whereas Kundu and Cohen do it in the first chapter itself. Okay. A scalar quantity, you all know that. A scalar quantity has only a magnitude, has no direction. Examples of this would be density, temperature, concentration. Okay. A vector is any quantity that has both magnitude and direction. Examples are position vector, velocity vector, forces, etc. Okay. A tensor is a generalization of this notion to higher dimensional systems, higher quantities. Okay. So example is a metric tensor. We will derive what it is later on, and the stress tensor, which we have talked about, and we'll talk about a little bit more again. Okay. So you can think of this sequence of generalization of ideas: a scalar, just a magnitude and a unit; a vector has a magnitude and a direction associated with it; and a tensor has a magnitude, a direction, and another direction. There are two directions associated with it. Okay, with a tensor. That's a second order tensor. Then mathematicians, of course, love. Then we can have a second order. Why can't I have a third order, fourth order, fifth order? So they develop the whole field of tensor mathematics. But we don't need that. What we will need, we'll just take and understand the symbol and be able to use it. Okay, so what is a vector? An example, as I said, of a vector is a position vector. So here you have a coordinate 1, 2, and 3. These are the three. It's a three-dimensional space, and in each one of the coordinate directions, I have a unit vector A1, A2, and A3. These are vectors of length 1 and pointing in the x1 direction. A2 is a unit vector of length 2. The magnitude of the vector is 2, and its direction is pointing in the x2 direction. These are called basis vectors or reference vectors. Why do we need them? Because it tells us the direction. Its magnitude is 1, it tells us the direction. Go in this direction. So when I want to tell an address of a particular point in space, okay, point P, how can I do that? This is called a position vector. You can graphically represent this by this line. connecting the origin to that particular point, P. And that P has three numbers, x1, x2, x3. And they can be written in a vector form. So whenever I write it in boldface, it means it's a vector. So that position vector x is equal to a1, x1 plus a2, x2 plus a3, x3. Okay. What does it mean? It simply means in the a1 direction, you walk a distance of x1. That is the magnitude. Then turn in the x2 direction, walk a distance of x2. Then turn in the x3 direction, walk a distance of x3. You will reach that particular point. So to reach that particular point, I'm giving you the coordinates, what you need to do to address that point or to access that point. So mathematically, you can write it in this way, or you can write it as a collection of three numbers, x1, x2, x3. These are called the components of the vector, right? So the unit vector itself will have a component of 1, 0, 0, meaning in the x1 direction, its unit is 1. It has no components in the x2 and x3 direction. So these unit vectors are independent of each other. You cannot write a1 in terms of a2, because a2 has 0, 1, 0, a3 has 0, 0, 1. So there's no way you can combine to express a1 in terms of a2. These are called, anybody remember? Linearly independent vectors. So to represent a vector space, you need to have a set of basis vectors that are linearly independent, meaning one cannot be expressed as a combination of others. Okay, that's the basic idea. So that's a vector. Any question on that? That's a position vector. So similarly, we will have a velocity vector v, and you can write this as a1 v1 plus a2 v2 plus a3 v3. What does that mean? Its velocity component in the x1 direction is v1, its velocity component in the x2 direction is v2, etc. Or you can write it as a collection of numbers v1, v2, v3. So we define this because we have need for them. We have to address a position vector, or we give a velocity vector, or an acceleration vector, etc. Now, coordinate transformation is an important idea. Okay, so here we are talking about rotation of an axis. Okay, so I have one coordinate indicated by x1, x2 component. Okay? It's a two-dimensional representation. We can generalize this to 3D, but let's just understand it in 2D first. So this is x1, that is x2. Then I have a new coordinate. I call it x1 prime, x2 prime. They are slightly tilted, oriented away from that. Okay. Now, just because I have changed my reference point, my point P that I'm interested in, position vector, is going to be the same. It doesn't change. So my question is, how do I tell you to go to P when we both are talking in x1, x2 reference point? Then that's very easy. I just need to tell you, go a distance of x1 in the first direction and go a distance of x2 in the second direction, you reach that point. Then I'm talking to you, and I have a different coordinate system, 1 prime, 2 prime. So I need to tell you a different set of numbers, x1 prime, x2 prime, so that you reach the same point. And that would be, go in this direction a certain distance, and then go in that direction. You will reach the same point. Whereas for the first person, I have to tell, go this way, and go that way, you will reach the same point. So there is a relationship between the components, x1 and x2, and the components in the new coordinate, x1 prime and x2 prime, that are related. So we need to be able to do this coordinate transformation. More than fluid mechanics, where this is used most is in video games. If you ever look at 3D video games representation, if you are taking a person and moving them one person to another position, they have these transformations built into the hardware so that they can do these calculations so quickly, so easily. Okay, this kind of a coordinate transformation in 3D from one viewpoint to another viewpoint, rotating, translating. Okay, so there are basically transformation matrices that will transform or rotate or stretch or whatever. So we need to be able to figure out what these transformations are. Now, let me ask you, are these familiar to you? Can I go faster, or do you want me to go slower?
Same speed.
Same speed? Okay. So I need, now from now on in this lecture, you need to go back and spend that 7 hours, okay? Because I am going to kind of talk conceptually about how to do it, but you need to do the math once by yourself, okay? So here, I said that there is a relationship between x1, x2, and x1 prime and x2 prime. keeping the position vector invariant. The position vector should be the same in both the coordinates. So what are the components? What values of red I should give? What values of blue I should give? So that you reach the same point in two different coordinate frames. So if I know x1, x2, I should be able to calculate x1 prime, x2 prime. That's not a difficult task. Conceptually, it's a very easy task, really tedious. Okay? So even in your textbook, it shows it only for 2D, and so you go and do it for 3D. Okay? So how do you do it? You do it by simply recognizing I want in the new coordinate the distance OD. X1 prime is OD. But OD I can decompose into OC plus CD. Okay? OC I can calculate it in terms of X1 from this triangle. So he defines alpha 1, 1 as the angle between the two coordinates. Remember, there are four coordinate lines here. 1, 1 prime, 2, 2 prime. So if I want the cosine of the angle between 1, 1 prime, that will be cos alpha 1, 1. If I take cosine of 1, 2 prime or 2, 1 prime, so there are four combinations. I need to calculate the cosine of all the four angles. Okay? And I can express this transformation in terms of them. But it's basically a trigonometric relationship. So the first part is this OC, which is given by x1 times cos alpha 1, 1. And then the second part is CD, but CD is the same as AD. Okay? And this AD I can get from this vertical triangle, once again recognizing that this alpha 1, 1, that alpha 1, 1 are the same. Okay? So that AB is going to be then given by x2, which is this vertical line, the red line, times sine of alpha 1, 1. And then you can say, okay, alpha 1, 1 is 90 minus alpha 2, 1. So I can put that, and then I can say sine of 90 minus alpha 2, 1 is cos alpha 2, 1. Okay? So a series of trigonometric transformations like that, you can express x1 prime as x1 times c1, 1 plus x2 times c2, 1. What is c1, 1? Cosine of the angle between 1, 1 prime. What is c2, 1? Cosine of the angle between 2 and 1 prime. Okay? So you can calculate this cosine of the angles because you know what is the rotation, degree of rotation. So that's the transformation. You can do the same logic on x2 prime, and you can get x2 prime in terms of again x1 and x2. Now, the general this is what you may find difficult. Okay, the generalization is very quick. So he shows you that I can attain x1 prime in terms of x1 and x2. I'm going to now write it in a compact form as summation of xi ci 1. Because the second index here remains the same, 1. The first index is first 1 and 2. The nice thing now is, if I can accept this, when I go to 3D, what's going to happen? All I need to do is change this into 3, from 2 to 3, and take the cosine of the angle between all the 3 coordinates, 3 old coordinates and 3 new coordinates. Okay, so I'm setting this up as a vector matrix product, because all this cosine of the angles is going to form a nice 3 by 3 matrix. Okay, so I can construct that matrix, and this is what I said is programmed into these 3D game simulators. Okay, so you can translate an object, you can rotate an object, things like that. Any questions?
What's C21? Is that just a variable?
C11, C21 are all cosine of the angle. So here, x1 times cos of alpha 1, 1. Cosine of alpha 1, 1 is this angle. Okay, the first index refers to the old coordinate, the second index refers to the new coordinate. So it's a cosine of the angle between 1 and 1 prime. So cos alpha 1, 1 is equal to C1, 1. Okay? And if I have cos of alpha 2, 1, that is what I will call it a C2, 1. What is that? That would be the angle between x2 and x1 prime. You understand that? No? Let's go back then. Do you understand this part? That equation. Okay. So in that equation, so in this equation, this is basically distances. Right? You understand that? So now I'm making a symbolic substitution. Cosine of alpha 1, 1 is what I call C1, 1. So it has two indices, 1 and 1, right? So that says that is the cosine of the angle between the vector 1 and the vector 1 prime. So it's this angle, right? And similarly, when I go to this one, I got sine of alpha 1, 1, which I translated into cosine of 2, 1. Use this one, okay? So now this is C21 is cosine of alpha 2, 1. What angle am I talking about? I'm talking about the angle 2 with 1 prime. So this one. So the first index refers to the first coordinate. The second index refers to the new coordinate. So when I say 2, 2 is with respect to the old coordinate. And the second index is 1, that is the new coordinate. So this is alpha 2, 1. Okay? Is that clear to everybody?
So C means zero.
Cosine. C basically is a cosine of the angle. And the two indices tells you which two angles.
And
Okay.
the first one is the first coordinate.
Right.
The prime.
Yeah, the primed coordinate. Right. Yeah, exactly. That's what it is. This is where, to understand these details, you need to put those extra 7 hours. Okay. But once you accept this, then it becomes very easy to do coordinate transformation in a general 3-dimensional case. Okay. And it's particularly easy to program it. You don't have to calculate it. You just need the formula, and it calculates all these angles. Okay. So if x, which is equal to x1, x2, x3 in a 3-dimensional case, and x prime is x1 prime, x2 prime, x3 prime. So the coordinate is rotated. Okay. Then I can calculate all these 9 angles. Now I have a 3 system. Previously I had a 2 system. I have a 2 by 2 matrix. Now I will have a 3 by 3 matrix of all the possible 9 cosine of the angles between those coordinates. Okay, so first we said, being lazy, I am going to put a summation and write this as xj prime equals summation over I xi cij. Next we go, and this is called Einstein's convention, and which says I'm not even going to write the summation symbol explicitly. I'm just going to write it as xi cij. Here we call I as the repeated index, meaning it repeats exactly twice in the formula. If any index like that repeats in the formula, it implies that there is a summation over that for all 3 possible values. Okay? It's just a matter of convenience, and it is very annoying initially. When I introduce that, students find it very difficult. Okay? But get used to it, because in the literature, in textbooks, in papers in fluid mechanics, you will find this used very liberally. Okay? So you need to, I will give the first exercise, in fact, the assignment part of the exercise will be trying to get familiar with this index notation. It's called the index notation. Okay? So whenever one index repeats twice in a product, a summation is implied. That means you're going to sum over all possible values of that particular index. Okay? Now, this equation 2.5 tells you that if you give me coordinate values in the old coordinate, and if I know all the cosine of the angles, I can calculate the coordinate values in the new coordinate prime so that I reach the same point. Okay? The question can be reversed, meaning if you give me the coordinate values in the new coordinate, can I express them in the old coordinate? That is, you give me x prime, can I give x back to you? So if you give me x, I can carry out this multiplication, I can carry out the summation, and I can give you the values in the new coordinate. But you can also give me the values in the new coordinate, I can give it back to you in the old coordinate, because it's basically the inverse relationship. Okay? Once again, the meaning for Cij or Cji still remains the same. It's a cosine of the angles between the old coordinate and the new coordinate. And here again, I is a repeated index, but j is a free index, meaning j appears only once in each term. Okay, I repeats, but j does not repeat. Okay, so when an index repeats, summation is implied, meaning you have to sum over all possible terms. When an index appears freely, it means that you need to take each value of j equals 1, 2, and 3. So this actually means that there are 3 equations in there. J equal to 1 will give you one equation, j equal to 2 will give you one equation, j equal to 3 will give you one equation. Do you want to take a minute and write it out in an expanded form? I just want to make sure that you understand what I'm talking about. So if you write it out, I think it will reinforce.
Why j equals to 1 is right?
Because I have three components, right? I have x1, x2, x3, or x1 prime, x2 prime, x3 prime. So if you give me x1, x2, x3, I should give you back x1 prime, x2 prime, x3 prime. So I will have three equations, one for each component. Okay? That's why j equals 1 gives you the first component, j equals 2 gives you the second component, etc. Do you understand how to write it out, or you want me to explain or show? I'm still not able to gauge how much you understand and how much you're just accepting.
Can you explain that? Do you call out that stuff?
No, you have to put numbers for them. Okay? For example, when I'm expanding for the first component of this equation, I would write it as x1 equals c11 x1 prime plus c12 x2 prime plus c13 x3 prime. That is the expanded form of that particular equation for the first component, that is for j equal to 1. So j is 1, is kept as 1 in every term of that, but I is a repeated index. So I is 1 in the first term, and remember summation, so I put plus, I equals 2 in the second one, but j remains 1. And then I equal to 3, j remains 1. Is that clear? Thank you. Anybody else need an explanation on that? You should be able to do that for j equal to 2. What will that give you? It will give you x2 equals c21 x1, c22 x2, and c23 x3 prime. Okay. If you understand this, then the notation becomes fairly simple to handle. But if you have difficulty with it, you need to work out a few problems. Okay. So here, for example, when I write something like this, Pij equals Aik Bkj, Pij will be called a second order tensor. So the number of indices in a symbol refers to the order of the quantity. If it has no index, it is a scalar. If it has one index, like x1, xi, it is a vector. If it has two indices, it's a second order tensor. If it has three indices, it's a third order tensor, etc. Okay. So here Pij is a second order tensor, and that is equal to writing it as Aik Bkj.
Actually, and the Buoyancy is scalar.
Scalar, right.
1 is a vector, and 2 is a...
2 is a second order tensor, 3 is a third order tensor, 4 is a fourth order tensor, etc.
There's nothing like first order tensor.
First order tensor is a vector. Is a vector. Yeah. Zeroth order tensor is a scalar. Right. Okay. So when I say Pij, I have two free indices, and each index can take all three possible values. So I actually have 9 numbers, a collection of 9 numbers. If I have only one index, I have a collection of 3 numbers. Those are the components of a vector. So these are the components of a second order tensor, P11, P12, P13, P21, P22, P23, etc. Now, how do we define the product? For example, when I put a dot in between, it's called a dot product. Okay, and which is the repeated index in that expression on the right hand side? K, right? K appears here and here in a product. So K is called a repeated index. That means summation over K is implied. I and J are free indices. They will take each value. So for example, if I put I equal to 1 and J equal to 2, I'm calculating this component of the tensor on the left hand side. How do I calculate it is given on the right hand side, the rule. And the rule is I have to expand this. So if I have to do this, the value of I equal to 1, J equal to 2, I will write P12 as A11 B12 plus, help me out, what would the next one be? 12 B22 plus A1 3 B3 2. That is the meaning of that right hand side. Repeated index and free indices. That's how it is used. It is nothing but a matrix product that we normally use. Simply the first row and the second column. The free index 1 and 2 indicate which row and which column to take, and the repeated index says take the corresponding products and add them up. A11 times B12, A21 times B22, and then A13 B32. Okay, so take the product and add them up. So you have to do this for each value of I and each value of j, and that will fill this entire 3x3 matrix on the left hand side. Okay? So the operation with tensors is not that difficult. If you understand and accept the definition, you should be able to do these calculations. Any questions? Yeah. What is K? K is the repeated index, so that means it will take all possible values. We'll have K equal to 1 first, K equal to 2 second. For example, here K equal to 1. The next time K equal to 2. The next time K equal to 3. Right? So it takes all possible values in one sum. So you need to sum them up because it is a repeated index. Whereas I and J are free indices. So they will take just the same value. Okay, 1, 2, 1, 2, 1, 2. They remain the same because I am calculating only this component by fixing I equal to 1 and j equal to 2. If I want to calculate this component, I need to fix I equal to 3 and j equal to 2. And again, apply summation over k. So sometimes this repeated index is called a dummy index because it doesn't have to be k. You can call it p. I can write it as IP BPQ. The result will be the same. Do you understand what I mean? The meaning of that will remain the same. Yeah.
Do the free indices need to be defined?
Define meaning, you are free to choose the symbol. So once again, instead of having ij, the meaning will remain the same if I put LM. That's what you mean, right? If I ask you to get a particular component, you need to make the choices for that symbol. Okay? But if you are writing this expression by yourself, you are free to use any symbol for the indices. But you must be consistent. For example, I cannot use L1 here and then ij here. If I have Lm as two free indices here, every expression must have an L and an M. Right? Because the rank of this tensor must be the same as the rank of that tensor. Right? So if I write as PLM equals ALP BPP, that will be a wrong expression because P repeats 3 times and M doesn't appear at all. These are the kind of things I'm going to give you in the first assignment, an exercise whether you can check for errors. In fact, we'll probably get to some think, pair, share kind of an exercise on this. Any other questions? Now, there are two ways of writing these equations. One is the index notation. The other one is called the Gibbs notation. Both are used in both the books. Okay, in Buoyancy as well as in Kundo. So this notation will be called the Gibbs notation of writing the same expression in boldface without an index. Okay, so this would be a vector, and that would be a tensor. That would be a vector. This is a dot product. Okay, so what this tells you is if you give me x, I can give you x prime. Okay, and there is a dot product. A dot product is equivalent to having a repeated index in the index notation. Okay, and similarly, if you give me x prime, I can give you out x. Okay, in fact, there is a relationship, because if you give me x and I calculate x prime, and if I take that x prime and put it into the next equation and I want to go back to x, I should go back to what? The original x, right? So if I do the substitution here, what you will find is x prime equals c transpose dot x, but x is equal to c transpose dot c x prime, right? So x prime and x prime must be 1. So c transpose dot c must be equal to the identity matrix, okay? Or similarly, c transpose must be equal to the identity matrix. That is, the transformation is unique. You'll go back to the same point. Now, the stress tensor. This is one of the reasons why we deal with a second order tensor. I think we already talked about it once, but because it's a difficult concept, let's talk about it one more time. What is a stress tensor? Now, position vector we can understand, we can all relate to, because we use it all the time, okay? Simply, when you give the coordinates, if I'll meet you there in a certain street on a certain avenue intersection, that is giving you the coordinates, right? So in GPS, for example, you give the latitude and the longitude. Those are coordinates. Arbitrary reference points that we build so that we can communicate with each other. Velocity vector we understand because we can feel the velocities. But stress is a more difficult concept to understand. It is a force per unit area, and force is a vector. There's both magnitude and direction. Area is a vector. That may be difficult to understand, the concept of area being a vector. What do we mean by that? How do we identify an area? If you give me an arbitrary shaped area, the way I can identify that is by saying that its normal is pointing in a particular direction. So we always give the area by its normal, because normal is uniquely defined. If you give me a surface, I can draw a normal to that, and that at that particular point, the area is locally well defined. Okay? So if you take, for example, a cube as a control volume, areas are well defined in this case. Okay? So here you have x1, x2, and x3, the three coordinate systems. So this surface, the front surface, has a normal in the x1 direction, right? So its normal is pointing in this direction, n1. And the force on that surface could be acting in any arbitrary direction. There is a force acting on the surface, but it could be acting in some direction like this, F1. Okay, I have to resolve that in each one of the three directions. In the first direction, and in the second direction, and in the third direction. And that is why I need two indices. One index to identify the surface, the second index to identify the direction of the force, the component of the force. That's why stress tensor has 9 components, because on each surface it has 3 components. The force has 3 components, and there are 3 surfaces. Okay, here is another surface, and there is another surface. So on each one of the surfaces in this figure, we are identifying what are the forces. For example, this force is tau 11, this force is tau 12, that force is tau 13. So the first index refers to what? Direction of the surface. And the second index refers to the direction of the force. So that's why it's not a vector, it's more than a vector, because there are 2 directional components. Because it is stress is force per unit area, area is a vector, force is a vector. Okay, is that clear? So as you shrink this volume to a point, just like velocity at a point is well defined, and it must remain the same. It is a physically meaningful quantity. So if I resolve in one coordinate system and you resolve in a different coordinate system, we will get completely 3 different set of numbers, but we are talking about the same velocity vector. Same thing for position vector. So in fact, we define the transformation in such a way that the position is uniquely defined, velocity is uniquely defined. Any physically meaningful quantity should remain invariant as we change the coordinates. That's one of the basic principles. Same thing applies to stress, because stress is a physically meaningful quantity. So if I define stress tensor, the 9 components of stress tensor in one coordinate, and if you are working in a different coordinate, we should be able to transfer that information from one coordinate system to another coordinate system. And those transformation rules are exactly the same. For a simple rotation, you use the same cosine of the angle. Okay? So this is how we would represent a stress tensor. So tau 22 means force acting on surface 2 in the second direction. Tau 23 means force acting on the second surface in the third direction. And this is how stress components of a stress tensor are transformed. Okay? So remember, now take a look at that and tell me whether it makes sense. Identify what are the free indices and what are the repeated indices. How many equations are there in that particular one? It's a very compact way of writing. That's why it's so popular. What are the free indices? M and N. What are the repeated indices? II appears twice, JJ appears twice. A repeated index can appear only exactly twice in a product. So here we have a product of three terms. In the product of three terms, a repeated index cannot appear more than twice. Then the definition is ambiguous. Okay, so it can appear only twice. So you understand that very well. How many equations are there then? 9. Because each value of m and each value of n will give you one equation. So m is 1, n is 1 gives you one equation. M is 1, n is 2 gives you another equation. M is 1, n equal to 3 gives you another equation. Three indices can take one at a time, all three possible values. Right? So there are 9 equations. And this is a Gibbs notation of writing that. And remember, a dot product is equivalent to a repeated index. I just threw this now. Fourth order tensor. A equals M, N, P, Q. Okay, so that's all it is. A fourth order tensor will have 4 free indices. Okay, so in this expression, we are transferring a fourth order tensor from one coordinate system to another coordinate system, from original to primed, okay, using the cosine of the angle. So what are the free indices? What are the repeated indices? How many equations are there?
Three or
60?
16.
What did you say?
64.
64? I guess the answer is staring at you there. Each takes 3 values. Right? Each variable takes 3 values. 3 components. Right? So 3 times 3 is 9, times 3 is 27, times 3 is 81. So there are 81 equations in just one line. It's a very beautiful, compact way of writing. It's called Einstein's summation notation. If you understood all this, and let's just look at Aij equal to. Write this in in symbolic form. What symbols on the right hand side would make sense? Let me call it this C, put this indices. JK. Or KJ, whatever. The meaning you have to be careful when you're writing it. But that would be a consistent index notation. There is no physical meaning attached to it yet, but that would be a consistent index notation because I repeats on the left hand side, J and K are free on the left hand side. So you must have a J and K free on the right hand side. So the result of that would be a second order tensor. So product of 2 second order tensors, the result will be a second order tensor. Okay, Aij, Bik. I guess it's the same thing, right? I repeats J and so I could write it as D, J, K. Aij, Bjk. What would that be? See? Ik, right? J is a repeated index. So all these cases are resultant is a second order tensor. The next one is Aij, Uj. it will be CI. What will be the resultant? It will be a vector. Okay. So what we have is a product between a tensor and a vector. A dot product between a tensor and a vector. So if you have to write this in index notation, you would write this as A dot U, and that is equal to C. And this is, we will see this when we have tau as a stress tensor dotted on N as the surface. Okay, what is that going to give you? Tn, the force acting on that surface. It's a vector. But the dot product between a vector and a tensor, the resultant is a vector. Okay, and this would be the same thing, C, J. So the next question is, how do we, I guess we are almost out of time. Okay, maybe we'll stop here and continue. I will put up an assignment with some of these, but I think I wanted to complete a little bit more in terms of vector calculus also. Okay, this is vector algebra basically, algebraic expressions, and so proving some identities and stuff like that. But you may just get started, but I will make the due date so that you have 1 week from Tuesday. By Tuesday, we should complete this section and then move on to developing. These are basically tools that we are trying to understand, and then we'll have to write Newton's law of motion for fluids using these symbols. Okay, we have to write the continuity equation, momentum equation, heat transfer equation, and mass transfer equation. We will develop those in these forms. Okay, so I think we can stop there now. Any questions? The pace of this lecture was okay because it is getting a bit more mathematical, right? And it will get a lot more mathematical if we solve differential equations. But if you're okay with the speed, we'll keep continuing. Okay.